Scooby-Doo, looking for you. Scooby-Doo, where are you? All the time we're here, waiting for you. Couldn't have a show without you.
For the next several videos, I would like to define the idea of a function and be able to look at a diagram like the one pictured and determine if it's a function or not. Look at a set of ordered pairs and determine if it represents a function or not. Look at a graph and determine if it represents a function. And finally, look at an equation and determine if it represents a function. Because functions are important in math. It's a notation and they have special properties. And so we want to be able to determine if we have a function. And in that case, we can use certain properties that apply to functions. So what's important here is a function is a relation that has the property that for each element in a first set, okay, so I'm going to underline that each element in a first set, and that first set's called the domain, corresponds to exactly one element in the second set. And that second set's called the range. And so when you're looking at here, you have a first set, that's in the blue. The elements in the first set are A, B, and C. So we could say the domain is A, B, and C. The second set is in yellow. And if I list those elements, I know they're hard to see, is X, Y, and Z, and that's called the range. Okay, now what I want to look is to see if this diagram actually represents a function. So if we take each element in the first set, does it correspond to exactly one element in the second set? So A is an element in the first set. It corresponds to X, and that's only one element in the second set. So A is good, okay? If we look at B is an element in the first set. Does it correspond to only one element in the second set? Yes, it does. It corresponds to Y, and that's only one element. And finally, C is an element in the first set, and it corresponds to Z, which is only one element in the second set. So this definitely defines a function. Now let's look at another example. It says, does the following mapping represent a function? So here we go again. We're going to take a look at the first set called the domain, and I'm just going to use capital Z to represent the domain. And the domain has two elements in it, A and B. And the range, I'm just going to use a capital R to represent range, has three elements, and they are X, Y, and Z. Okay, now the question is, does this mapping represent a function? So again, for each element in the first set in the domain, does that correspond to exactly one element in the second set, a range? Well, check this out. A corresponds to two elements. It corresponds to X and Y, which means automatically this is not a function. In math, it still applies. It's something called a relation, but it is not a function. And we do run into problems in mathematics like that. But when we learn about special properties of functions, then it wouldn't apply to this particular problem. Okay, a third example here for you. Again, that each element in the first set corresponds to exactly one element in the second set. So we're trying to determine if this represents a function. It still has a domain, A, B, C, and a range, this time X and Y. So for the element A, does it correspond to only one element? Yes, it only corresponds to X. For the element B, does it only correspond to one element? Yes, it corresponds to Y. The element C only corresponds to one element. It happens to also be Y, but that doesn't matter. It is okay for the answer to be the same for two different input values, okay? What's not okay is the last problem where the input value shoots out two different results. You see the difference? So A mapped to two different answers. That's not allowed in a function. But if the answer is the same for two different input values, that is allowed for a function. So the answer is yes, this is a function. If you had to explain why, you could say for each element in the domain, there's only one element in the range. Now, it's hard to read, but for each element in the domain, there's only one element in the range, which is basically what the function says. Okay? And then the last example that I have with these diagrams has a domain of A, B, C, and a range of X and Y. Now the question is, does this define a function? In other words, each element in the first set corresponds to exactly one element in the second set. Okay, so let's check out each element again. A corresponds to only one answer, X, so we're good there. B corresponds to only one answer, Y, so we're good there. But C doesn't correspond to anything, which means no, not a function. Now, if you had to explain why, we just did, right? C does not have an answer. More specifically, C does not correspond to anything in the second set. Now we want to be able to extend this idea to a set of ordered pairs. You know what an ordered pair is. An ordered pair has the property that X is the first value, Y is the second value, or you could say the first value is the horizontal axis, which is the independent variable, and Y is the vertical axis, or the dependent variable. Okay, so one thing I want you to think about here, X is the input, Y is the answer. Another way to think about this, the definition of a function is for each X, there's only one Y. That is just another definition for a function. For each X, there's only one Y. So let's take a look at these four separate problems. Again, we have a set of ordered pairs. Notice I put 4 ordered pairs in each one of them. 4 is not significant. It just happens to be the questions that I made up. But for each X, is there only one Y? So let's take a look at our X's one at a time. So in the first list, in example A, the first X value is blue. It's 1. Okay, and the answer is 5. I don't see anywhere in the list that 1 gives you a different answer. So 1 gives you 5, 2 gives you 7, 3 gives you 9, and 4 gives you 11. If I turn that in to the list we had before, this would be 1, 2, 3, 4. That's your input or your domain. Your Y values are 5, 7, 9, and 11. That's the way that works. And 1 maps to 5, 2 maps to 7, 3 maps to 9, and 4 maps to 11. Now, you certainly don't have to draw it that way. The things I'm going to ask is what is the domain and what is the range? The domain is your X's, your input. 1, 2, 3, 4. The range is your Y values, the output. 5, 7, 9, 11. And most important, is this a function? Yes, it is. Because for each X value, there's only one Y value. Okay, so next, example B. Let's list the domain again. Domain is the X values. In other words, 1, 2, 3, and 4. The range is the Y values in the list, 3, 3, 3, 3. Now, do I need to list 3 4 times? I do not. It's just 3. That's the only answer we could possibly get. Now, the question is, again, for each element in the first set, so for 1, how many answers do we get? Well, 3. That's the only answer. For 2, we only get one answer. It's 3. For 3, we'll only get one answer. It happens to be 3 also. And for 4, we only get one answer. It's 3. It is okay that these Y's repeat. It is okay that 3 is the answer for all of those input values. What's not okay is if we had an input or an X value that we got 2 different answers on. So this is yes, it's a function. Again, if I had to explain why, I could say for each X, there's only one Y. So I just return back to this definition. Now let's look at C, our red example. Here we go again. Domain. Let's list the domain. I got a -1, a 2. Notice there's a -1 again, so I'm not going to list it again, and 0. Okay. The range, the output, or the y values is 5, 4, 9, and 1. These don't have to be listed in a specific order. Sometimes it's nice to have them from smallest to largest. I just listed it in the order it shows up in the problem. Okay. Now, the question is, for each element in the first set, so for each number -1, 2, and 0, do we have only one answer? And if you're astute, you notice this. Pay attention. -1, 5, and -1, 9. That's a problem, right? That means for -1, we got two different results. We got 5 and 9. That's not allowed, so this is not a function. Okay, so maybe if you're doing a quick check, when the y's repeat, like in the green example B, that's perfectly okay. When the x's repeat and it gives you two different y values, that is not okay. Okay, so for our purple example, example D, again, we have a list for our domain. That's the x values, 1, 2, 3, 1. Okay, I don't need to list 1 again. Now that ought to make you a little nervous because when the x's repeat, it's a problem. The range gives you 1, 3, 9, and 1. I need to list the 1 again. So typically, again, when the x's repeat, it's a problem. But in this case, it's actually no problem at all. And why would you think that? Well, 1 maps to 1, and the same exact point is listed again. 1 maps to 1. So actually, that's not a problem at all. For x equals 1, we get 1 both times. So that doesn't give us two different x values. 1 just gives us an answer of 1, even though it's listed twice. So this is yes. This is a function. For each x, there's only one y value. All right, so we have a brand new problem here. This time, we don't have a diagram. We don't have a set of ordered pairs. They gave us an equation. So does the equation represent a function? And over here to the right, I have some steps for you. So step 1, isolate the y variable. So this isn't the first time you've ever done this right. You've got to get the y by itself. And then it says if for each x, there's more than one y, and this plus or minus is kind of a separate thing I've got out there. So for each x, if there's more than one y value, or you get a plus or minus, the equation does not represent a function. So let's do what it says. We're going to isolate the y variable, which means I got to get this y by itself. I don't want to move it. I want to move everything else. So I need to move the 2x. I'm going to subtract 2x from both sides of this equation. Of course, they cancel there. That leaves me with 3y equals. Now, at this point, you have a choice. You can write it as -12 minus 2x. I often end up writing the x term first and put the constant in the back, so -2x minus 12 is fine as well. I still have to get rid of the 3, so I'm going to divide this whole thing by 3, which is actually the same thing, and by the way, those cancel, is saying y equals 2/3 x minus 12/3. So I put that 3 underneath each one of these terms separately. And then finally, I can simplify. That'd be -2/3 x minus 4. So that's step 1 done. Now for the analysis. If we plug an x value into this equation at the bottom of the screen, do we get more than one y value? And if you think about it, no you don't. And it just as an example, let's just try to plug in, say, x equals 3. So that give me y equals -2/3 times 3 minus 4. The 3's cancel. That give me -2 minus 4, which is -6. How many answers is that? That's only one answer. Okay. Now, we can't do that for every single x value. There's an infinite number of x values. But we can think about it and go, okay, well, I don't care what I plug in there. It's not going to suddenly shoot out two different results. I'm just going to have to do the math. It's going to combine together, and it's only going to give me one answer. So I'm going to show you one that's not a function in a minute, and you're going to feel better about it when I'm saying. But right now, that does not have two y values for any particular x I decide to plug in. I just use this example. You don't even have to show me the example. You don't have to pick a number to think about it. But if it helps you think about it, you go right ahead. But the answer is yes. For each x, there's only one y value. All right, let's try it again. I have same directions. Does the equation represent a function? So I've given you an equation. I left the rules over here, over to the right. We're supposed to isolate the y variable. And if for each x there's more than one y, then we don't have a function. On the other hand, if for each x there is only one y, you do have a function. So what you're looking for is plus or minus. If you get a plus or minus in your answer, bad news, you don't have a function. All right, so I've got to isolate the y. The first thing I'm going to do is subtract 2x from each side of this equation. That cancels. I have 3y squared equals. Now up to you. You could write negative 12 minus 2x, or again, just like the last problem, I tend to write it with a descending powers order, basically. The x term first and then the constant in the back. I have to divide by 3. Remember, you could split that up on the right-hand side. It gives me y squared equals negative 2/3 x minus 4. It feels a whole lot like the last problem, except I've got a y squared. And if I'm supposed to isolate y, I have to get rid of that square. So I'm going to take the square root of both sides of this equation. Now, some of you know right off the bat, if you take the square root of an equation, if you use the square root as a tool yourself to solve an equation, you must write plus or minus. And that's because when you have an equation that says y squared equals something, whatever you plug in for y could be positive or negative and still give you that answer. Okay? If you think about something simple, let's go over here to the right. If I told you that x squared equals 9, and you tell me what two answers would make that true, or what answer, well, x equals 3 is the obvious answer, right? But x equals negative 3 works as well. So if we took the square root of both sides, I would only get x equals 3 as an answer, but we know negative 3 is an answer also. So to remedy that situation, we always throw that extra plus or minus when we use the square root as a tool. So we're going to do it now as well. Okay, so my result is y equals plus or minus square root of negative 2/3 x minus 4. All right, now, is this a function? No, right? Why not? Because I go right there, plus or minus. Because if I plug in a value for x, I'm going to get two different answers, okay? So let's say I just plug in negative 3 for x, okay? Well, we've got other issues in this problem, so don't get hung up on that. But any x I plug in, I'm going to get two separate results, which means we do not have a function in this case, okay? If you dig deeper into this problem, you might find an error. Don't do that. Just focus right here. Don't worry about the negative under square root or anything like that. It's just a separate issue, okay? So this is not a function. Okay, here we go once again. Does this equation represent a function? Does it not look just like the last two problems we did, maybe only slightly different? Well, let's find out. Okay, so I subtract 2x squared. I subtract 2x squared. So recall the very first step of determining if an equation represents a function is to simply isolate the y value. Okay, so I subtracted 2x squared from both sides. I rewrote the right-hand side. You could write it as negative 12 minus 2x squared. I tend to put the variable part first. Now I divide everything by 3. I could just divide the entire right-hand side by 3, but it's easier to split it up. So negative 2/3 x squared minus 4. All right, y is isolated. We are done with this, but we haven't done our analysis yet. If I plug in an x value right here, like say 0, I'm only going to get one answer, negative 4. If I plug in x equals, say, 3, then I would square it to get 9. The 3's would cancel. That give me negative 6 minus 4 is negative 10. Again, only one answer. It does not have that dreaded plus or minus. So yes, this is a function. Okay, it's that plus or minus that causes us problems. And now the last problem of the video, and the last of one of these types of examples, once again, does the equation represent a function? Okay. I know this looks almost just like the last three problems we did. I'm making small tweaks so we can come up with a conclusion at the end that might help us out a little bit. I'm supposed to solve for y. Okay, so let's do that. So I'm going to subtract 2x squared from both sides of the equation. Cancels. I get 3y to the third equals negative 2x squared minus 12. I divide everything by 3. Gives me y to the third equals negative 2/3 x squared minus 4. Now, very similar to when we had a y squared in our problem, we have to take the square root of both sides. In this case, we have to take the cubed root of both sides. Okay, so I do the cubed root of y to the third is equal to the cubed root of negative 2/3 x squared minus 4. So the cube and the cube root cancel to give me y equals the cubed root of negative 2/3 x squared minus 4. Hold up, hold up. Do we need to put the plus or minus in here when we take the cubed root of both sides? We had to when we took the square root, didn't we? Well, some of you know right off, and some of you are like, I don't know. Don't we always put it if you do something like that? Well, let's find out. Let's do an example that you know. All right, and an example that you know is, let's do x to the third equals, let's do 8. Okay, now let's think about a number that would work. All y'all know x equals 2 works, right? Because 2 to the third equals 8. The question is, does the negative 2 work as well? Well, no. Negative 2 to the third is negative 8. So when you do the cubed root of both sides, you don't have to put the plus or minus because you don't get two results. There are not two answers that'll make that true. So plus or minus not required, which means for this particular problem, yes, it's a function because you don't have plus or minus out front. For each x you plug in, it's only going to spit out one answer, and that's it. Okay? All right, now, we can kind of summarize. If you go back and look at these problems, I gave you a problem with a y to the first. I gave you a problem with a y squared. I gave you a problem with a y to the third. Okay, we could even do one with y to the fourth. The question would be, do we put a plus or minus if we have a y to the fourth and have to take the fourth root of both sides? And the answer is yes. Okay, so summary, here we go. If you have a y to an odd exponent, like y to the first, y to the third, y to the fifth, you're going to be dealing with a function. Okay, now you got to be careful. I'm talking about basic polynomial equations going on right here. So I'm not dealing with trig functions or anything like that. If you're thinking about other types of functions, this is just this basic stuff we've got going on here, polynomial equations. If I have y to an even power, that is not a function because you have that plus or minus every time you try to get the y by itself. Now the question is, what happens with x? I'm going to flip back real fast on the video here. Look, no, that's too fast, right? So that one is x to the first power and y to the first power, and y, it was odd exponent, so yes, we had a function. This next one, y is to the even power, so no, we don't have a function. But look at this next one. X is even and y is odd. Well, it turns out whatever x is raised to is insignificant. It doesn't matter at all. It is what the y is raised to. So if you want to use the little cheating rule, and again, what I really wanted you to do is solve for y, okay? But if all you can remember is the cheating rule, then here's your rule right here. I've got kind of highlighted there. If y is odd, you have a function. If y is even, you do not have a function. And of course, I'm talking about exponents, not whether y is odd or even, but whether the exponent is odd or even. Okay, so that wraps this video up. If you'll come back for the next video, we'll talk about how to find out if a graph represents a function, and then more details from this section on functions.